Mm.
So fundamentals of electromagnetism.
Mm.
We have Lenz's law, which is going to tell us in which direction you're going to have electric current induced if you have a changing
Mm.
magnetic field. Right?
Mm.
So current is induced such that it works against the change in magnetic field. It tries to compensate. So
Okay.
so here, like it tries, like initially there was no field at all, and you move this magnet closer. So it tries to
Mm.
counteract against that. It creates a field in the opposite direction, so that it cancels out and becomes closer to zero. In the opposite
Mm.
case, when it's moved away, it tries to give another field in the same direction to keep the original field, the coil.
Okay.
Right hand rule, which gives, like when you have a current, what is the magnetic field produced around it. So if it's a vertical conductor, then it's like rotational around, like around circular patterns. If you have a circular coil, in the
Mm.
middle of the coil, especially at the center, it's perfectly straight magnetic field line.
Mm.
Faraday's law, it quantifies how much voltage is generated based on the change in magnetic flux.
Mm.
Yeah, it's a mix of drives and FOE kind of. So byproducts of Faraday's law, here we have the force acting on a current carrying conductor in a magnetic field. So F bar is I times L bar cross B bar, but I don't think we use this anywhere in the course. So just background. So
Mm.
this F bar is created in the motor, and that is why you have a torque. We will look at that. DC
Okay.
motors. DC motor uses the force exerted on a current carrying conductor, like I said before. So what happens is, in the beginning, so we have these permanent magnets and we have these brushed connections for the north and south pole. So initially, static magnetic field is created, and
Mm.
it has some repulsion. Then it starts rotating, and then because it's rotating, there's a change in magnetic field. Like the permanent magnet's field is vertical in this direction, and when it
Mm.
rotates, the amount of field passing through the coil is changing. So it tries to compensate that.
So which one is the coil? The yellow ones?
Yeah, the wires, the yellow ones. Yeah, that's the coil. Orange, yellow ones.
And there is a magnet in between
The
the
magnet is
coil.
on the sides, so the north south is the effective field being generated in the coil itself.
Hmm.
So we have
Okay.
these external magnets for excitation. It's called north
Hmm.
pole, south pole, because it's using permanent magnets to create this external field. Because going back here, to have this force, you need a current, which we make in the coil, and we need a magnetic field, this B bar.
Hmm.
And that B bar is what we're creating here using these permanent magnets. So north to south there is a magnetic field. So the
Okay.
field line would be in this direction. That would be the direction of the field lines.
North pole to south pole.
Yes, always. And
Hmm.
here, since we are supplying current, this coil is also acting as a magnet, and that is the north and south poles created by this coil.
You're talking about the left picture, right?
Left picture itself, yes. So you see this north pole, this south pole, it's
Hmm.
created inside the coil because of the current being supplied. So that is why these north poles are repelling each other and it starts rotating. But once it starts rotating, what is happening is the magnetic field is changing. So some forces are created on this conductor. If you use the right hand rule, you will find that there is a torque in the direction being mentioned. So here the force will be like this, and there the force will be like this, which is why you have a net torque. So it's a rectangular loop, it's a simplified coil, and there is a magnetic field passing through it in this direction. So like X, meaning the field is passing into the plane and it's not coming
Hmm.
out of the plane, it's going into the plane, and I'm feeding a current in this direction. Now if we apply the right hand rule, center
Hmm.
finger along the direction of current, field pointing inwards.
I cannot see your head.
Okay, okay, one moment. uh, So center finger in direction of current, field is pointing inwards, and then torque is in this direction. I think I'm making a mistake. Just a second.
Left hand or the right one?
Yeah, so Fleming's hand rule is kind of generalized. So here you're looking at the case of a motor, so we use the left hand. But if you're looking
Mm.
at the case of a generator or dynamo, then you use the right hand.
Okay, okay.
Yeah, it's weird like that. But back to the topic. So here we use the left hand rule. Middle
Hmm.
finger. Is your video off?
Yeah.
Okay. So middle finger through the direction of current. So let's say let's look. I'm looking at the presentation from the side of it. So current is
Hmm.
up on the left arm. Field is
Hmm.
downwards. Is passing into the screen. So torque.
Hmm.
What? Why is it to the left? It should be
I
downwards. Oh, why? Ah, okay, okay, right. Why would it be downwards? It is to the left.
yeah, because what I remember is like the force or the torque is in the third dimension, like not in the
Yes,
same.
yes. Here, what
Because
is happening is the field is in the third dimension. So the force is in the second
mm,
dimension itself. But if you look at
mm,
this one, F
mm,
bar is I times L bar cross B bar. Let's do that. But even if I do that, I think I will get the same one. So this is L bar, and in the third dimension is B bar.
mm,
If I do right hand rule for cross product, I get the same answer, force to the left. So that's
mm.
confusing. Force to the
No
left,
worries.
and there it will be force to the right. So that means the coil is expanding. Hmm. That is true. A current carrying coil will have some outward forces. Ah, okay. Now I remember. In a motor, at this point, it's actually making no torque on the shaft itself, because you see, on the left side, the force is to the left, the right side, force is to the right. But imagine that coil was vertical, right? So if I
Mm,
look at the same top view, I'm just seeing this one rod,
mm,
but actually it's like that. It's in 3D. So the upper wire is still carrying. Okay, I made a small mistake. So let's do it there, there. Okay, the upper wire is in that direction, lower is in this direction. Left hand rule for motors. Current
mm,
is upwards, field into the plane. So then you have force to the left.
mm, mm,
If you do it for the lower wire, it will be force to the right, and that is creating a net torque. Got it? So apologies for my confusion. It's been a while, but there's the difference between left and right hand rule. You can use right hand. Is there an internet issue?
like, would we use all these in the
In drives,
question?
no. But just to give some background, I gave that. You don't need to know all
No.
this for drives.
Yeah,
But yeah,
because
that's how
I
the
think,
motor is working, especially DC motor.
yeah,
So you can
I'll just
see
watch
that the
the,
torque is not constant. It keeps changing based on the angle. So if you make like a plot,
your screen is not sharing.
oh yeah, right. To share, I will share my whole screen. Yes. So if you plot torque versus time of the motor, it will actually be a sine wave. No, but it's not a full sine wave because we have commutator. It's like this.
One more question, like, Why aren't we using the force?
We are using the force. So in this case, when the coil is in this orientation, is flat, like it's in the plane of the screen, and the field is always in the same direction passing through the screen. In this case, there is no net force. This force and this force cancel. I mean, the forces are always cancelling, but there is no net torque also. In the other extreme case, there is the maximum torque. So that is what is happening. So this origin point, so this is, let us say, case A, case A, case B, and this point is case B.
What I'm trying to ask is like, if I initially due to this we'll get a force, right? And then if we multiply it by the radius, then we'll get the torque.
Yes,
Torque is due to the rotational motion of the coil, right?
correct.
Because the coil is like rotating inside the magnetic field.
Yes.
Okay. Okay, that's why we are taking the torque. Okay, okay.
Yeah, yeah, yeah. Actually, good question. There are motors which use the force directly. They are called linear motors. So they just have
Hmm.
like they're on a railing. They have
Hmm.
vertically, like along the line, magnetic fields being created, and they move.
Hmm.
They use the force directly and they just move. So like maglev trains, they are basically a linear motor. And nowadays aircraft carriers, new ones, they are using the same linear motor concept. They are very
Hmm.
powerful if and they need strong magnetic fields to create this power. So they're very energy intensive. That's why maglev trains also they take a lot of power.
Okay.
So general equations. This is the drives part which is needed.
Hmm. Hmm.
So UT is the total voltage. Do I have a
Hmm.
circuit maybe? Yeah. So look at the circuit. This
Hmm.
this whole thing is UT total voltage. Yeah. UT is
Hmm.
UI plus IRA. So let me
Hmm.
continue. So let us have this UT. The armature has a resistance. Like we call the windings of the coil windings which are rotating as armature, and it has resistance.
Hmm.
So there is going to be some voltage loss across this resistance, which is IR as per
Hmm.
Ohm's law.
Hmm.
And as the motor is spinning, there is also an induced voltage because of Faraday's law, which we saw, like d phi b by dt. There is an induced voltage.
Which is UI.
UI exactly. And if I plot UI versus omega, it's basically linear, I think. It is. It is.
So the picture on the slide
Which slide?
of the circuit,
Uh,
the one you showed,
yeah, yeah.
what is this? Is what is this shunt field like
We will get to that.
below
Just
the
just
slide?
one moment. Just one moment. I will get to that.
Hmm.
But in a motor, so far based on what we have seen, we have this
Hmm.
resistance of the coil, and then because of the rotation, there is an induced voltage inside the coil, which is acting against
Hmm.
the current being supplied. So that is also a voltage drop effectively. That is why we have this UT equals UI plus IRA.
Hmm.
The electrical power, of course, it's the supply power. It's current times UT, but the mechanical power is just current times UI. So this I square R is wasted.
This is the loss PL, I
Is
guess.
Yeah, it's a loss.
Hmm. Okay.
These small losses that are being ignored, we will look at it right now. If you want to make larger motors, DC motors, it's not a good idea to depend on permanent magnets. Today we have quite strong magnets available, but back in like
Hmm.
the 60s or 40s, they didn't have these strong permanent magnets. So instead, what they did, they had a separate coil winding which created this magnetic field. So you see here we have some permanent magnets creating the field. Instead, you can
Hmm.
have these coil windings which create magnetic field.
What do you mean? Like if we
So this is
like.
one separate coil winding. There's a rotor connection. Nothing changes there. But I
Hmm.
replace the north pole with one coil, south pole with another coil which is taking current in the opposite direction. So this has field lengths going like that. that has field
Mm.
lines going like this. So it's acting as effective north pole, effective south pole. So and then that becomes the field, external magnetic field.
So basically, wrap the coil on the magnetic,
We
like on
replace
the
the
magnet.
magnet. There is no permanent magnet because it's not strong enough. So instead, we have a like iron core and then we wrap it with copper to create this coil,
Hmm.
strengthened coil, and then it creates the magnetic field.
Okay.
So that is the shunt field being discussed here. And this shunt, it takes a current. Yes, of course, it's a real device. It takes some current, but it's really small. So I shunt much smaller than I total. So you can ignore it. That's what we do. We ignore the current consumed in the shunt. And there are two
Okay.
types of motor. In this shunt excited motor or separately independently excited motor, other names for it, this shunt field is in parallel to the armature. But in the next type of motor that we will see, can you hear me?
Mm-hmm.
Okay.
Mm-hmm.
The next type of motor we will see is different. This field is instead kept in series with the armature. Each of it has its own benefits. We will look at that right now. So, like I mentioned, the coil is connected in parallel to the DC supply to produce the magnetic field, runs at almost constant RPM, irrespective of power, and irrespective of load. It has a very low starting torque, not very low, but lower starting torque compared to wound field motor. The
Mm-hmm.
magnetic flux is constant because the shunt field is always getting the same total voltage if you have a battery, and it's always making the same magnetic field irrespective of what speed you are running, what load is there.
Mm-hmm.
In this way, the wound field is better because in the wound field, if you have a very high load, then the field created is stronger, and at a lower load, the field created is weaker.
Okay.
This has very good speed control because you just have to change the voltage. The field becomes less strong because of a smaller current, and the torque is lesser. Current flowing through the shunt is neglected. Condition for maximum power is reached when the back EMF UI is half of the supply voltage. But at this case, you have low efficiency. Uh, okay, so here I have given the condition for max power for a shunt
Share
and.
your screen,
Yes,
please.
right, right. Uh, said this. Yeah. So this is the condition for maximum power of a DC motor. The maximum
Mm.
power will be reached when the back EMF UI is half of the supply voltage. But when that is happening, it means the efficiency is quite low. It's actually 50% theoretically because UR, the voltage across resistor, is UT minus UI, and that is UT by 2 because UI is half of UT. So half the power is just being spent on the resistor because they are all taking the same current. You see this? The voltage across resistor, if it's equal to UI, that's the case for maximum power. But at this point, you have very poor efficiency. So usually we don't run it at that case because lot of heat is being generated. The coils can get damaged.
Mm.
There is this thing called a ballast resistor. We can put that in series because in the beginning, the armature is not spinning, right? It's fixed. The motor is not moving. So when you connect it to the supply, it can have a sudden current surge, which can damage the supply. The battery could be damaged, or the wires can overheat. So we use this thing called ballast resistor. Just an extra resistor in series. So we have an extra resistor in series. It's called R ballast, and this resistor it controls how much it decreases the amount of current flowing, and once the armature has started spinning a bit, we then disconnect this ballast and we make connection across it, so that there is full current flowing, and then the current surge is avoided, and it gives this soft start feature that there is no sudden increase in torque.
Just a like normal question, like How is the shaft connected to the motor?
The shaft,
Like,
the shaft is just connected to this armature, this coil.
yeah,
You can look at some images.
yeah. Can you show me an image?
Yeah, this one is really good. Yes. So this is the shaft.
Screen is not there.
Okay, okay. Only my PowerPoint was shared. So let me share the whole screen. Yeah. So this is a very good image because it shows everything. So on the left half of the image, you're looking at the commutator setup. Those are the commutator rings, and this coil is sliding inside these rings. On the right half
Hmm.
of the image, we have this bearing which is carrying the shaft. The
Hmm.
commutator part, these are the commutator brushes. This is graphite, and it can wear out over time. That's why you eventually have to replace the brush or the motor itself. So that's
Hmm.
the commutator ring. These are the coils, coil windings, and that at the end is a fan for cooling for like a big motor. But for a small motor like in this size, this is the kind of coil you will see. There is no fan, nothing. I think there isn't even a bearing. It's just a plastic casing that's holding it in
Okay, the
place.
shaft is basically inside the motor.
Yes, shaft is inside.
Okay, okay,
Or
okay.
maybe there
Okay,
is a bearing. Not sure. Depends. Alright. So moving on. So understood what is the case for maximum power and ballast resistor, why it's used?
yeah.
Okay. So this is the torque versus speed diagram, which is a very useful thing to know about any motor, so that you know when it has what torque and what you get as that speed increases. Because for a
Hmm.
fan, if you have a fan, if you just connect this DC motor to a big fan, for a fan the power demand looks exponential. Okay, let me look at show torque demand first. Torque and torque proportional to n square for a fan.
Hmm.
So in that case, if you want a large range of speeds which is working with this motor, you would not choose this motor because the variability is too much and you need more and more power as the RPM increases. But here it's reversed. More and more torque is needed as higher RPM, but here it's giving lesser and lesser torque at higher RPM, so it's not a good choice. But if you just need a single operating point, then you know this curve of your fan, like the actual fan blade itself, and you know the curve of the motor. That intersection point will be your working point. That will be the RPM at which it's spinning. We have a question like this, we can solve that.
Okay.
So here TS is the starting torque. It looks higher than nominal torque. Yes, it is. But compared to the wound field motor of similar construction and same voltage supply, the starting torque is lower. Tn is the nominal operating point. Like this is the nominal RPM, nominal torque. As you go to higher RPM, the torque goes all the way till 0. And that N0 is the rotational speed with no load. It's called ideal speed.
Okay. So why is the torque going in negative?
Because somehow, if you take a DC motor, normal DC motor, if you just don't connect any load to it and it's just connected to the supply, it will be at this point. But somehow you're increasing the RPM. How can you do that? By supplying torque to the shaft. You are somehow giving some torque to the shaft to spin it up. Which means now this DC motor, instead of giving you torque, is taking torque. So that is negative.
Okay.
And DC motor, for a given direction of supply, polarity is never going to turn in the opposite direction. So for it to turn
Yeah.
in this like negative n, okay, that is meaningless. This is meaningful. You can still use the same modeling, but this part is not meaningful, I think, because when it's negative RPM, then it's clearly you who is supplying the torque. Then it's like a dynamo case. It changes. Okay, so
Yeah.
that's the torque speed diagram. There are more diagrams. Okay, equations first. This UI, this induced voltage, it is perfectly linear, like I mentioned before. This K1 is called a motor constant. We use this term K1 for UI. There are other Ks as well. We don't look at that in this course. But for the induced voltage, the proportionality constant we use is called K1. It's the convention. Phi is the magnetic flux. We usually don't calculate that. It is usually going to be constant in a shunt excited motor. So K1 phi you can keep it as a term, and most of the equations you see here just K1 phi as a single term.
Hmm.
Under no load, under no load, what is happening is no torque is being made. No load. So no torque. Therefore current tends to 0. Therefore UR tends to 0. U induced tends to UT. Understand? Because to get torque you need current. If there is no current there is no torque, and at no load point there is no torque, which means there is almost no current flowing. Very small amount of current is flowing.
Hmm.
So ut
Okay.
equals ui equals k phi n naught, and n naught is the rotational speed at no load. These are the generalized equations between torque and rpm. Just look at this specific equations.
Hmm.
This U supply voltage not going to change. We're giving same constant supply. K1 motor constant not changing. Phi not changing. Resistance not changing. 2 pi constant. So if you look at
Hmm.
this, torque is something, some K plus this whole thing is also a constant, because you can see all these terms are constant. So I will call it M, this with the negative sign. So K plus Mn, which is exactly the equation of a straight line. Y equals mx plus c. And that's why here we have a straight line in the torque versus RPM diagram.
Hmm.
So they all
It's
fit together, because they are all consistent. So that's the equation. You will need these equations. Keep note of that. This TS starting torque is just a special case when n goes to 0.
okay. I like this is okay. Okay, let's move on. I want to do some questions because this is really boring.
Okay.
This,
Torque is proportional to current, but you need the basics.
okay.
We will come back to this later. Permanent magnet excitation, it's the one of the cases. It just means phi is constant. So this k and phi terms are removed from the equations,
Hmm.
and then the equation is simpler. That's it. But this torque being proportional to current is always true, even for the motor with the shunt excitation. Torque is proportional to current.
Okay.
So let's look at this question.
Hmm.
Here we have this same machine, electrical DC machine. In one case it's acting as a generator. We are rotating the shaft. In the other case it's acting as a motor. The resistance of the
Hmm.
armature is known, is 0.5 ohms. Full load
Hmm.
armature current is 20 amps. Find the induced EMF.
Hmm. Okay, so I guess.
So motor case is straightforward, just repeating. We use the same
Hmm.
equation. This 220 volts is being supplied, 10 volts spent on resistor, 210 on the 210 volts are being dropped across the coil itself because of the induced magnetic field at high RPM. In the generator, the voltage is coming from the UI side, and the current is flowing in the other direction. So this is the motor case. Current is flowing in this direction, let us say.
Hmm.
In the generator case, it's opposite direction.
Hmm. So the just the formula changes to
So
U.
UI, let us say, is this direction. here the ui direction changes and the current is also flowing in this direction. So the formula changes, and if you solve this, you get uh, induced EMF is asked ui equals ut plus IRA, which gives us 220 volt plus 10 volt is 230 volt.
Hmm.
This is not a core part of the syllabus based on what the professor has taught,
Hmm.
but it is still very much something he could ask, so I'm covering it.
Okay.
Now I will show it quickly what's changing. So here it's just direct application of the same equation that we saw here. This same torque versus N equation. When I change this value phi, this armature flux, not the armature flux, the flux, the magnetic flux, we are changing
Hmm.
the constants. Both K and M are changing. This K
Hmm.
and this M. So that's why the intersection point with the x-axis is changing and the slope is also changing. But if I change only armature voltage, you see this u term is only on the constant. So the slope doesn't change, just shifts parallel shift.
Hmm.
Armature resistance changing, only the slope, wait, both should change. Hmm. Both
Armature
should have
resistance is
changed.
RE, right?
Yes, so both of
Hmm.
these terms should be changing. So I'm not sure what is happening here. Why does the N naught remain same? Ah, yes, because N naught is independent of RA. Right, good point.
And not.
N naught, the ideal speed RPM, is not changing when you change the armature resistance. Torque is still
Hmm.
going to zero irrespective of what armature resistance you have at full RPM. But the T versus N curve, the slope itself is changing and also the constant. That is why the y axis intercept, which is what is given by the constant, is changing. So the starting torque is changing. And here is just a combined case of all three. No, I'm not going to discuss that. But basically, if you
One.
know this equation, you can give these kinds of graphs. What will happen if flux changes? Flux is phi. What happens when the armature resistance changes? What happens when the voltage changes? You can make these graphs.
So one question is this equation n is equals to u over k1 into phi minus ra into 2 pi over k1 squared into phi squared into t torque.
Mm.
We are saying if I change the ra, it wouldn't change n.
Yes, when RA is changing, there is no change in N.
Is it possible?
Kind of like, I mean, it's not directly like that.
Well, I think it doesn't matter.
Both equations are the same. Basically, they're representing the same thing, just N in terms of T or T in terms of N. And mostly in real life, it makes sense to have torque in terms of RPM. That's how we think. At higher RPM, what happens to torque? That's what we think. We don't think what happens to RPM at higher torque generally. So this is a more useful equation. The second one. Now let us do a further question.
Hmm.
I will switch to the one note. So you have solved it correctly. What you did was you used the mechanical power equals current times ui, and the current is
Hmm.
given, mechanical power is given. From that you got ui, which is 363.63 volts. And then we take the equation ut equals ui plus IRA, substitute the ui in that, and you get the armature resistance. Now
Hmm.
in the next step, you need the idling rotational speed. So here remember the
Generator.
relationship between voltage and RPM. U is K phi n. Go for the shunt case because it's not permanent magnet. Yeah, U is K1 phi n. Use that. And the no load case UT
K1
equals UA.
this one UI is equals to K1 idling rotational speed
Yes, yes.
is the question. So idling rotational speed in generator
Hmm.
mode. So we are going to K. So for like what I'm trying to ask is, but we don't have magnetic flux in K1.
Hmm. Doesn't matter. Just use proportionality. Keep the whole K1 phi as a proportionality constant and you can solve. That's why they have given in the generator case the RPM.
I understand.
That's
I
what I
don't
mentioned when I
understand.
said earlier we don't split this K1 and phi within the context of this course.
Hmm. Okay, so in generator mode running with 10 RPM, it's like delivers the current of 100 ampere. The idling rotational speed in generator mode.
So in this case, what they're meaning is what is the idle speed you need just to create the voltage, this 400 volt,
Hmm.
without giving any current, so without actually supplying any power.
I don't know how to solve it.
Okay, then I can solve. Shall I start?
Yeah,
Okay. Yeah, I'm recording. So you correctly found out the armature resistance. I think what was it?
it's 0.33 ohms.
0.33 ohms. Correct. So B idling rotational speed N naught is asked in generator mode. So idle meaning I tends to 0, no current. Therefore,
Okay.
ut equal to ui. Keep that for now. And we also know at n equal to 1050 rpm, current equal to 100 amps. And the ut is not changing. Ut is 400 volts.
So UT becomes UI if there is an
in
idling
in the
case,
in the
but
idle condition, yes, ui has to be ut for it to idle, because if you are rotating the shaft any slower than that, then the induced voltage is below the network voltage and it starts consuming current from the network, which we don't want. We want to make a generator.
okay.
So we use the equation ui equals ut plus ira for a generator. 400, no, not 400, some ui which is k1 5 times 1050, right, bracket u
Mm.
ui equals k1 phi n.
Mm.
K1 5050 equals ut 400 plus ira, which is what, 100 amps
Zero.
multiplied by 0.33 ohms. So k1 phi equals, so this is 33, 433 volts divided by 1050 rpm. So this gives you k1 phi.
Mm.
And then you look at the idle case. ui equal to ut.
Where IRA would be zero, right? Because
IRA is 0 exactly.
okay.
So K1 phi n equal to 400 volts. Substitute this value, solve. So N equal to 400 volts divided by 433 volts divided with 1050 rpm, not N, 1050 rpm. What does that give us? 400 by 433 into 1050, 969.9. So 970 rpm. So you need to spin the shaft at this speed at least to ensure the generator is reaching the network voltage, and as you spin it faster it starts making current.